Okay, so we're going to start off with this problem, and it is a related rates with some Riemann sums and some integrals. So it's a good segue from last unit into this unit. So in part A, it says estimate the radius of the balloon at t equals 5.4. So what we want to do is we know the radius at 5. It was given in the problem. So the radius of the balloon is 30 feet when t equals 5. So at 5, it was 30. But now I need to take into account what's happening, with that extra 0.4. So we're going to add the change when the radius is 5 over that amount of time. So dr dt, basically I might go back and label this as my change in radius over time. That's the derivative. So at 5, it said that it was changing by 2, and then the amount of time was going to be 0.4. And this is a calculator active question. Hopefully you don't need your calculator for that one, but you do have it available. So you could just do 30 plus 0.8, and that is given in feet because your radius is measured in feet. And I think I need to give an explanation on this one because it says, is your estimate greater than or less than the true value? Okay, so this is similar to I think it ended up being in problem 13 from here. You need to do a little function analysis, and my pictures aren't always great, but I'll give it a whirl. We know two things about this. We know that it's concave down, okay? So if I was just kind of sketching something that was, let me kind of do it just off to the side. So if you have something that's concave down, right? And you are going to draw in your derivative, okay? So your derivative, if something is concave down, if you had to draw a tangent line to that, notice that your tangent line, no matter where you draw it, is going to be above the graph. Versus if you were concave up and you drew a tangent line, it would be below the graph. And you're going to kind of use that. It shows up a bit in some of these problems. So I just have that drawing of something that's concave down, and I know it's concave down because it told that to me. And because concave down, the derivative is above it, so the derivative is going to be an overestimate. Okay? So I would say overestimate because it's concave down, so derivative is above because concave down. And I just kind of drew that picture there, okay? So we've got that, and hopefully that would be enough to get me my 2 points for part A. And now the part B, this is the review. So it says, find the rate of change of the volume of the balloon with respect to time. When t is 5, indicate units of measure. So notice here, like it specifically told you to indicate units of measure. So that means they're going to be counting that against you if they don't. So just kind of making sure you're answering the full question at the end there. So we're going to say B. What I kind of tackle these as what do I have and what do I want. So it says find the rate of change in the volume. So you want the change in volume over time, specifically when t equals 5. That's what you want. Okay, so I write, that's what I want. What do I know? Okay, well, they gave me the formula for volume. Ooh, that was nice of them. They don't always do that. So they told me that volume was 4/3 pi r cubed. Now notice this volume, you will not need to use product rule when you take the derivative here because this pi is not a variable. It's not like when it's one of the formulas that has height and radius where you have to use product rule. This pi is a constant, so you will not need to use product rule there. And yeah, we're going to go ahead and take the derivative of that because we want to know how that's changing, so we know this. So we could say that the derivative of the volume with respect to time is going to be this times this gives you 12 over 3 pi r squared. Use implicit differentiation there, so you tack on that dr dt. And when t equals 5, right, so now we're apply t equals 5, or you could say plug in, okay? So specifically when time is 5, so dv dt, okay, well that's going to be 4 pi, that part's easy. Okay, the radius, so we're going to go and plug in, and keep in mind, back up here, this is your dr dt. So you've got your dr dt at t equals 5 is going to be 2, and the radius is 30. That was given up above. So we've got 30 squared, and then from the table I got that 2, because when t equals 5, the dr dt was 2, the derivative of the radius. And this was a calculator question. So then you can kind of put all that in. Be sure that you include your units to get credit here. So I got 7,200 pi in its volume, so that's going to be in feet cubed in per minute, right? Okay, and that was worth 3 points. So I'd imagine that you would probably get a point for, sometimes you get a point for just writing those things down, figuring out what you want, and then you probably get a point for an expression, and then a point for the answer. And then again, the units, they had said in the scoring guide that that was like a separate point to see if you had units on like all the parts. So notice that I, had labeled the feet there, the feet cubed per minute there. So that's how you'd get the other point. Okay, so then in part C, they're saying use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate the integral. Okay, so we know Riemann sums approximate the integral, so that's fine. So 5 subintervals, I am going to, let's see if I could write it over here and fit it. Okay, so we are going to estimate the integral. Okay, we'll say that. And it's an estimation, so it's going to be approximately, I'll just write it down here then. Okay, so remember, when you're doing the rectangles, it said to use how many? 5 subintervals. So if you are going up here, you'd say, okay, there's 1, 2, 3, 4, 5. There's no shame in that scratch work if you want to kind of show, the rectangles. I like that because then it helps me visualize, okay, the left-hand side or the right-hand side. So here it's asking me for the right, so I'm going to use this 4. I'm going to use this 2. I'm going to use the 1.2, the 0.6, and the 0.5. So those are what I'm going to use, and we'll figure out how wide each rectangle is. Your delta x is determined by this distance. So that this first rectangle here is 2 wide, and its height is going to be 4 because it said to use a right-hand Riemann sum. So it's going to be 2 times 4 plus the width of the next rectangle is 3. Oh, and I am not writing anywhere where you can see, sorry. So it would be 3 times 2, and then I'm just going to write down here because I ran out of room, and then plus, we're going to have the width of the next one, so from 5 to 7 is 2 times 1.2. The width of the next one is 4 times 0.6. And then the last one, it's just a width of 1 and a 0.5, because from 11 to 12 is only 1. Okay, so there's my setup. And then through some calculations, hopefully you can get that that gave you 19.3, and that's going to be measured in feet. And did it say something like that? Oh, it said in there specifically, using the correct units, explain the meaning of that in terms of the radius of the balloon. So that's one of the things that they're kind of coming up with. They really want you to be able to say, what does it mean? So here, this is the total change in the radius over 12 minutes. Okay, so you could say here that the radius changed a total of 19.3 feet over 12 minutes. So again, in words, that would be, this is the total change, because remember, integral is, the sum, the total change in the radius over 12 minutes. And that 12 minutes just came because the table went from 0 to 12 minutes. Okay, so we've got that. Okay, and then part D says, is your approximation in part C greater than or less than the integral from 0 to 12 of the derivative dt? So give a reason for your answer. So we want to know, is our approximation an overestimate or an underestimate? So I wouldn't be, ashamed to kind of sketch out a picture here. So for part B, or for part D, you need to basically figure out if a right-hand Riemann sum is going to yield an over or under estimate. To do that, you need to know if the original function was increasing or decreasing. How are you going to figure that out? You got to look back at the table. So what is happening over time? This radius is decreasing, so it's a decreasing function. So I know it's kind of a weird spot to stick it, but I'm just going to stick it right here. So D, it's a decreasing function. So if you need to kind of sketch out what that looks like, I don't know, just kind of give yourself some sort of a decreasing function there. And if you were to break that up into a few subintervals, and I know maybe that yellow's not very good, let me switch. So if you were breaking that up into some subintervals and you were going up and using a right Riemann sum means you hit it and then you go to the left. You hit it and then you go to the left. You hit it, you go to the left. So you would see very clearly there that it was an underestimate. Don't be afraid to sketch these out. It's going to be very challenging for you to remember, oh, a right-hand Riemann sum on a decreasing function yields an underestimate, okay? Just sketch it out. Sketch out a little picture, and that would help. So I would say right-hand Riemann sum on a decreasing function, on a decreasing function yields an underestimate. And let me just make sure I answered the full question. Is it greater than or less than? I answered that. Give a reason, because a right-hand Riemann sum on a decreasing function. Oh, I guess I don't need that S there. Okay, so we have an underestimate there. So hopefully that would be enough. And kind of go through and kind of see, did you, make sure you have all your units on this one. That gave you a point. I think this one was definitely very doable to kind of get, your 6 points there.